folks. So this is going to be a lecture without a live audience. and so please do send in questions if you don't understand anything. Organic chemistry tends to be one of those things that there are many different ways to describe what's happening. and so it tends to benefit from people's confused looks going, okay, let's try a different way to do this. Everybody learns it a little differently, and it's something that needs a little bit of work on in your brain to connect. Okay, so this is going to be generating epoxides as your substrates. So this is another synthetic tool to set up something that is extremely reactive, i.e. an epoxide, and then be able to use that epoxide to generate new additions in those SN2 style reactions that we had used before on epoxides. And so this right here is bromoethane going to the alcohol. Normally that'd be very difficult to do under these sort of conditions in any controlled manner. But H2O with DMSO as the solvent at 80 degrees Celsius, 8 hours, actually will give you 88% ethanol. And remember, when we did this before, we had found that it is actually quite difficult to attack the carbon on a bromide with something like a water. Okay, so notice right over here we have an epoxide, or another way of saying that is an oxirane. This is with NaCl. Notice that's neutral conditions. We don't have an acid here. We don't have a base. Normally we would have done this with an acid to open the epoxide and make that a better leaving group. But we're not doing it here. And so this right here then is methanol for your solvent. And what we're going to get is we're actually going to get a ring opening. And then that had the chloride attacking over here. This one right here is under basic conditions. We're generating an alkoxide right here. Notice that sodium is going to leave, leaving us with the negatively charged oxygen. This is actually a pretty powerful base and nucleophile. And so this is going to attack and be quite good at attacking here. But again, that's because we're under the basic conditions instead. Okay, so let's go ahead and look at the mechanism for this. That's weird, it froze. Okay, so right here we have the mechanism for an epoxide ring opening. Again, this is going to be the one with the strong nucleophile under basic conditions. Remember, if you were under acidic conditions, you would not be able to generate this strong nucleophile. It would get attacked by the acid, and you'd end up with just all methanol. Okay, and so here we have the basic conditions. This is going to attack one of these alpha carbons that's bonded to the oxygen. And remember, this is very analogous to having something like a carbonyl or having something like a alcohol that's going to be easier to break them off because it doesn't actually have to completely leave. Okay, so this is under basic conditions, so we're going to form the alkoxide here, the negatively charged oxygen. It's going to attack this one right here, which is that primary carbon right here, that first. Okay, and then we get the SN2 reaction. This is going to give us this right here, which is that methoxy group. And then we're going to have the alkoxide on the other side. Now note again, even though this is under basic conditions, we can generate the alkoxide under basic conditions. This reaction is still going to be unstable, and it'd still be an active reaction without that proton transfer. So we're going to need the final step to be a proton transfer with the solvent. Remember, again, the solvent's going to be what you have the most of, and so that's going to have lots and lots of that available to go ahead and end this reaction. And that will end the reaction. Now, note that one of the things that you may not be grasping yet, because it's just a lot of material all at once, and you don't get to make all the permutations among the material, is that if we have the solvent here is well matched with the alkoxide, and so this solvent, if this was to lose the proton to the alkoxide attacking species here, we'd actually generate the same attacking species. And so this is one of the reasons that you pair your solvents with your attacking species under these basic conditions. If we were to have used water or ethanol here, we would have generated a different attacking species under these basic conditions, and it would cause us problems, actually. In this case, we paired these with, this is the basic form of our solvent, kind of like using OH minus in water, or using the ethoxide with the ethanol. Okay, and so we go ahead and do a proton transfer step last, so we go ahead and put the H on there, making that alcohol, and now that's not as reactive, it's lower energy, and so we have pushed forward this reaction. You will note that we actually regenerate our methoxide here, our basic species here. So this is kind of an interesting thing, because this is, even though we've added one of those, we do regenerate it at the end, and so we can do the reaction again until we start running out of the substrate, the epoxide. Now, note that because the epoxides can undergo SN2 reactions, this is actually largely due to the fact that this is used to relieve that ring strain. So this right here, these epoxides are actually extremely reactive. And so you don't actually need such a great nucleophile with an epoxide. The epoxide is actually very high energy. So anytime you have a high energy starting, that energy barrier, so high energy starting, the energy barrier is always going to be easier to get over. If you're lower energy, it's harder to get over that energy barrier at the beginning. So these carbon atoms are going to be non-equivalent. They're both going to be chiral centers on this case right here. And these are the chiralities of those chiral centers right there. And so under neutral or basic conditions, a nucleophile will attack an epoxide at the less highly alkyl substituted C atom of the ring, i.e. the side from the side opposite the oxygen atom. So we're going to attack down here from the side opposite of the oxygen atom. It can't approach through the oxygen atom, so we have to attack from the other side, and it's going to be the one that is going to be the less highly alkylated side. And so you can actually see that right over here, where we attacked with the ethoxide this time, and then we finished it off with acidic conditions, actually. And so the ethoxide attacked over here from below, and that is where it ends up at. Notice this right here, this one's this one that came out towards us before. This one here is the one that went away from us before. This right here is this, and this is the methyl over here. And there we go. This is going to be the only substituted product in this case, because this one's going to be very, very difficult to attack with an SN2 mechanism, because that's so substituted. Again, remember, we're doing SN2 mechanisms. The more substituted it is, the slower the attack is going to be. And when you have two options to attack, if one's significantly faster than the other, that one's going to happen significantly preferentially. In this case, we're actually a tertiary carbon, and so that one's going to happen basically not at all. And that one's going to happen slower than it otherwise would, but much, 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 much faster than this one. Again, that's the less highly alkylated side that gets attacked, and again, it's a backside attack. It's going to lead to a Walden inversion, by the way, and so you will have that inversion of your stereochemistry due to the SN attack, just like we had seen before. And again, that's due to the steric hindrance of this. The only real thing that the epoxide does for you here is it just gives you a much higher energy substrate, and so this reaction goes much faster than it normally would. Note that the second step, where you add the acid in, is actually to give you the an acid to go ahead and do the proton transfer step and end this reaction. And so it takes the alkoxide species that was generated from the SN2 reaction, that natively charged part that used to be the epoxide, and this is going to then do the proton transfer step, giving us our alcohol and ending the reaction. Okay, so this right here is I'm just going to put this on the screen, what I would like you to do is, whenever we're doing video stuff like this, please pause it and actually try to work this a little bit. Because if you never actually try to work it first, you're going to have troubles whenever you try to do it on your own. It's much better to sort of work through and find where you got stuck and then see how somebody else does it. Okay, and so again, we have an epoxide, we have this NaOCH2, CH3, and then we add an acid to it afterwards. And so this is actually the exact same mechanism as we just did. And I'm going to just skip through this real quick because that isn't going to help anybody. All right. So again, when we put the NaOCH2CH3 in, this right here is going to dissociate and give us our base, which is the negative oxygen. And so that's then going to attack. It's going to attack the less substituted side, which is this one here. And then this oxygen is going to break its bond and take the electrons that were in that bond and form that alkoxide. And so we end up with this species at this point. Now note again, it's the backside attack right there that's going on to there. It has to be on the opposite side from this oxygen, which is why you always end up like that, where it's on the opposite sides of each other. And then the next step, the step 2, has the H3O+, which is that right there, and that is doing the proton transfer step. So we go ahead and take the electrons into a bond with that proton, leave the electrons on there, and that generates the water over here. And we get the alcohol here. So let's go ahead and look at it under acidic conditions. We can do a very, very, very similar reaction under acidic conditions. However, it's going to have a few key components that are different. So in this case, we again have our epoxide under acidic conditions. So we have concentrated HBr and water. And so what we're going to see here is we're going to see a nucleophilic attack at the more highly alkyl substituted carbon atom. So before, when we were on basic conditions, we got it on the less substituted side. Under acidic conditions, we're going to have it on the more substituted side. Now, the regiochemistry is going to be quite different from that observed under neutral or basic conditions. We're going to go after the more substituted side again. And so, why is that? Well, you actually kind of already have the materials for this. This is really just, we're taking specific cases now, and we're ironing out our understanding of these. We're doing those permutations, trying to get a more complete understanding. And so this is actually going to be where we do the proton transfer step first. And so under acidic conditions, we first need to generate acids, right? And so everything's going to go acidic, okay? Rather than generating things that are basic, like the alkoxide after the attack. And so we go ahead and get the proton transfer step first. The electrons on this oxygen, on the epoxide, are going to go into a bond with hydrogen. And then this is going to leave its electrons on bromine, generating the bromide. So the next thing that's going to happen is we now generated this protonated oxygen, which is a very good leaving group, and is going to give a lot of positive charge on these carbons here. Now note that because it has a very high positive charge and these bonds are getting very weak due to that oxygen being protonated, that generates a lot of positive charge. And so the one that can hold the most positive charge is actually the most substituted carbon. We're generating something that's very close to being a carbocation here and could in some ways be considered carbon-cation analogous. We're not quite doing it though. And so bromide is going to attack the more positive side that can hold that more positive partial charge. Again, you can think of it as in terms of stability. So this is going to be more stable with the charge over here. It's going to be more stable to go ahead and weaken that bond more and pull the electrons away more from over here. And so the easier one to attack is going to end up being over here, where the bromide is then going to give its electrons into a new bond. That's that coordination bond in an SN2 attack. And then the electrons in the oxygen carbon bond go on to that oxygen, leaving you with the alcohol. Again, note that is an SN2 reaction. And again, we're going to attack from the opposite side, away from this oxygen down here. And we're going to come up, and we're attacking from basically where we are onto that carbon, because this one's fading away and going to block that side. And that's going to give us our new bromide bond, our substitution product. Note that we don't actually have to do any more proton transfer steps because we had been doing everything acidic. And so when we break this bond, it doesn't get a negative charge. It goes from a positive charge over here to a neutral. And so we're actually at the stable state right there. So let's go ahead and look at some of the effects of protonation on that epoxide bond lengths. And so what we see here is when we go ahead and protonate this, this is going to greatly increase this bond lengths for these bonds. However, the one that increases the most is going to be the one that's on the more substituted side. That's going to give us a longer bond length, and that's a weaker bond. And the larger partial positive charge is going to happen on that more substituted side where it's more stable. And so, again, we end up with a larger positive charge that's more stable over there. And that's why our nucleophiles are going to attack there. It's quite analogous to the same thing that we had looked at in the carbocations again. It's just we're not actually generating a full carbocation. And in this case, it's interesting because we're generating a pretty large partial charge. Not quite a full charge, but a very large partial charge. And so the side that's more stable with that large partial charge is going to be the one that can get the nucleophilic attack. Note, however, if we had a tertiary carbon here, that would actually be very, very slow to attack, and so you'd have very slow SN2. It's still an SN2 reaction, right? So if you block off all the avenues to attack, it still can't attack well. So this is going to be the formation of epoxides. This is going to be via nucleophilic substitution, actually. And so this is a halohydrin, halogen, hydrin. And so we're going to be doing this under basic conditions, NaOH, diethyl ether, and this actually takes 24 hours. This is a pretty slow reaction compared to a lot of the stuff you've done. But this will generate 96% yield and an epoxide right there. And so when you generate epoxide there, you can then put almost anything you want in a pretty controlled manner, as you've seen. So this is actually going to be the mechanism for this. So we have here what would be have some acidity to it. So under basic conditions, this alcohol can lose its hydrogen to a proton transfer step, and that will leave a negative charge on this oxygen. Now note, because that negative charge in the oxygen is right next to a positively charged carbon due to this chloride, it's actually going to start sucking the electrons over into a bond with that. That same thing that we've talked about many times before, where when you have these partially positive carbons, they have that little orbital on the other side, if you remember. So it has a little orbital over here that's part of that hybrid orbital. It comes like that. And then that's going to have slightly positive charge, and it's going to pull the electron density from over here into something analogous to a bond. Now in this case, it will literally pull the electrons into a bond eventually. This is going to be an SN2 reaction that happens intramolecularly within the molecule. And so it's kind of an interesting case here. And so this pulls the electrons over into a bond here. This is going to form that epoxide, and then the chloride is going to leave with the electron density, and that's quite stable as a negative ion. And so we end up with our product over here. Now note that this is a pretty slow reaction compared to some of these other ones, but we get excellent yield out of this. This is actually quite thermodynamically favorable. Okay, so this is diazomethane. It's going to be the formation of the methyl esters. This is methyl ester, by the way. Here we have a methyl on an ester. This is going to be with treatment of carboxylic acid with diazo. Diazo means two nitrogens bonded to each other, which is what this is right here. Diazomethane. And so that's going to yield your methyl ester. And the acidic hydrogen atom is going to be replaced, which is right there, with that methyl group right there, the CH3 group. Notice that this right here is a nice ester, and this right here is your dichloromethane, or dichloromethylene, depending on where you're getting it from. This takes 30 minutes, gives you 90% yield, which is fast and a really good yield. Note that this actually generates N2 gas. N2 gas is the same gas you breathe. It's 70% of the atmosphere. So this actually generates rather benign products in terms of the gases it gives off, which is quite nice. So this right here is the mechanism. And so this is what a diazo looks like. Diazos are kind of interesting because they're triple bonded nitrogens with one of the nitrogens having another bond to like a methyl or ethyl or some sort of carbon chain typically. And that actually gives the nitrogen a positive charge. Now, nitrogen's fairly electronegative. And so these are not very stable. They're actually quite difficult to store or keep for any length of time. And they actually have an interesting resonance structure where you actually have a double bond and a double bond and a negative charge on that nitrogen. And so if you remember your Lewis structures writing these out, these are actually both what are considered high energy structures, right? And so we have this very high energy reactant here. We have right here a weak acid, so it can deprotonate fairly easily. And so what's going to happen here is this is going to act as our base here. We're going to deprotonate our carboxylic acid, and this first step is going to be the proton transfer step. And so diazos are bases. This is then going to give us the electron-rich atom right here, which is just that acetate or carboxylate, like you would normally generate in an acid-base reaction with a carboxylic acid. And so what's going to happen then is we're going to have another one of these diazos come along. And so this right here is the negatively charged. This carbon is going to be quite positively charged in here. Or another way of saying that is that it wants to pull electron density over to this nitrogen. Remember, it has this state as well, where it's pulling the electron density away over to this nitrogen. And so what we're seeing here is this is going to then pull that electron density into a bond here. It's going to leave the electrons behind on the nitrogen. And what really makes this SN2 step work here is actually this N2. This is about as excellent as a leaving group as you could possibly get. It's extremely stable. It's one of the most stable things on the planet. And then it's a gas, so it actually is going to evolve out of your solution and go off into the headspace and atmosphere. And so it completely leaves the vessel. It is the best leaving group I think we generate, period, at all. Far more stable than water. Incredible leaving group. Just absolutely excellent. And so this is largely what actually really drives this part of the reaction right here, is that the leaving group you generate is extremely thermodynamically favorable, about as thermodynamically favorable as you can get. This is why you don't burn nitrogen, by the way. Like if you look at, we burn oxygen in the atmosphere, which is only 20-something%, almost 21%-ish. And we don't burn the nitrogen atmosphere, which is 70s percent. So, did I say 21%? Wow, I'm mixing up my numbers really bad, but yeah, so 70s percent, 29-ish% for the oxygen. We don't burn the nitrogen because it is very stable. It takes a lot of energy to do that. And in fact, that's how you generate nitrogen oxides, which are trace amounts generated in like engine blocks. And they actually fall apart fairly easy if you give them some time under heat conditions. But that's smog, in case you're curious, is the NO typically, and NO2, which are the main components of smog. photochemical smoking, that is. Okay, so this is the amines. This is the primary amine right here is going to be where you have only one carbon attached to it. Secondary amines are going to have 2 carbons attached to it. Tertiary amines are going to have 3 carbons. And a quaternary, quote-unquote, amine is actually going to be referred to as a quaternary ammonium ion. And that's because once you've attached 4 things to a nitrogen, the nitrogen is going to end up with a positive charge, because the last thing that gets attached is actually going to have to use that lone pair on the nitrogen to form the bond. And so that is the primary, secondary, tertiary, and then quaternary. Notice the quaternary doesn't normally get, more often than not, you're not going to see 4th degree for quaternary, and you aren't going to see it, it'll be called out just ammonium ion. And maybe if you have to, you stress out quaternary, because the ammonium ion is always quaternary. So it's doubling up the information. This is some different examples of amines. Here we have an amino acid, actually. The amine's right there. This is the R group that determines which amino acid it is. And this one right here is what gives it the acid name, which is a carboxylic acid. This is histamine. This is actually a neurotransmitter. And so we can see quite a variety of amines, actually, on this one. Do note that the amino acids in histamine can actually be the quaternary salts as well. So if you've ever seen histamine salt or histamine HCl, that's actually the salt form of this. They put an acid to protonate it, and then that's ammonium ion. This right here is methyl orange. This is a synthetic dye, and you may have used this in a variety of different reasons, like as a detector or dye in whenever you're using, like in biology. I don't think you probably would have used it in general chemistry, though. This is pseudoepinephrine. Pseudoephedrine. This is the decongestion. And this is the amine right here, by the way. So we got that nice amine group. Alright, so let's go ahead and look at the nucleophilic substitutions, where we have the alkylation of ammonia and the amines. So here we have free ammonia. This is uncharged. It's a moderately strong nucleophile. Despite the fact that it's uncharged, you can then attack different alkyl groups. So here we have a bromol alkyl. It doesn't really matter what's on here, as long as it's not highly branched, because we're doing an SN2 attack. And so we go into the attack, we leave the electrons in the bromide, that leaves the leaving group. Notice we are then going to have that ammonium salt that generates first. This is under basic conditions because ammonia is actually a base, and so we're going to deprotonate one of the other ammonias. And this is then going to be that proton transfer step. This gives us the primary amine in this case. And we have our primary amine product. Note that if we have the primary amine, we have enough of our substrate right here, we can actually get another attack, because this is still a pretty good nucleophile. And so it's going to attack another one of these R groups. And again, bromide's going to leave in another SN2 attack. And so we'll get another alkylation on this amine. And that's going to do another proton transfer step, and we can get the secondary amine right there. Now, this can actually happen again, and it actually does this quite well, and so we can go ahead and alkylate this one more time, and we can get the secondary, primary, secondary, tertiary, and amines, and finally the quaternary ammonium ion as well. Now, note that it does get slower over time. It's harder for it to do it over time. And partially this is because you're going to have lower and lower concentrations each time of your reactants. And so the likelihood of it happening is going down each time. So your primary amine is going to be something like 57% if you have 3 equivalents you added of the NH3. And then you're going to get 25% to the secondary and tertiary is going to end up being 3%, and then the quaternary is going to be trace amounts. And partially this is because, notice we only added 3 equivalents to this, and so we're using this up each time. Okay, let's look at a large excess. If we put a large excess of the alkyl halide here, and we have our ammonia, we let this go for over 8 hours at 100 degrees Celsius, so we're really going to let this go. And what we can see is that over time, it's gonna, with a high temperature, lots of time, lots of substrate, we're actually going to get 87% of the quaternary ammonium ion, and that'll be the major product then. Okay, so let's look at the Hoffman elimination, another named reaction. Okay, so this right here is actually a Hoffman elimination reaction. The major product of the Hoffman elimination is going to be what's called the anti-Zaitsev elimination product, or the Hoffman product. So what we're going to have here is we're going to have our amine, and notice again that's a that's a primary amine, excuse me, and then we're going to have an excess of CH3I. And then the next thing that we're going to add to it is going to be a silver oxide, Ag2O, and then we're going to give it the heat. Okay, and so we're going to then heat it. And so that we actually form a elimination product again, a double bond here, and so that strongly suggests that we have an elimination reaction. It's going to occur where our leaving group will contain that nitrogen atom. There's 2 things that we need to really concentrate on here, though, that are a bit of a problem for what we're seeing here. There is, number 1, the amine group here is not a good leaving group. It is a terrible leaving group. It's actually very bad at it as a leaving group. So they do not participate as substrates in elimination reactions typically. The major product is also a terminal alkene. This is actually the less stable product normally. And so of the possible elimination products, which could have been here or here, we're getting the less stable one, the anti-Zaitsev one. And that's why this is referred to as the Hoffman product and the Hoffman elimination, because it's the one we normally would not see. So we need to reconcile these 2 things in our mechanism here. And so this right here is going to be our mechanism. And so the first thing we're going to get here is we're actually going to get an alkylation, and that's going to give us our ammonium salt here. Ammonium salt is this is the ammonium, and then this is the iodide, so that'll give you the salt all together. So what's going to then happen is we have this hydrogen that's acidic. It's actually going to go off onto the other amine we have. Remember, we have these amines right here, and so that's going to protonate another one of the amines. And that's going to then give us the alkylation. Now note that that same reaction can keep happening just like all the other alkylations, and so we get 2 more alkylations. Just do this again and again, and we get 3 alkylations total, giving us the quaternary ammonium salt. Now, once we get that actually has some degree of stability to it, and so what we can do now is we're going to go ahead and put in Ag2O. That's that next step of the reaction right there. So we go ahead and put that in, and what that's going to do is it's going to replace the iodide with hydroxide. And so now we're going to have hydroxide available in the solution instead of iodide right here. And so this is then going to start reacting with this, much as if you used ammonium hydroxide, gives you the free amine. That's actually smelling salts, in case you're curious. It's a kind of analogous reaction, but we end up with an elimination. And so what we end up doing is we react with this. That's going to react with this hydrogen right here. Remember, this is positively charged, so it's going to be pulling electron density away. And that's going to put electrons in between here. And now this amine is a much better leaving group, because it's already positive charge. When it leaves, it's going to leave with a neutral charge, making it much more stable as a leaving group. And so then this is going to give us our product right here, that primary alkene right here, that one that's on the edge. Okay. Let's look at the regioselectivity of this. That's the one part we haven't really reconciled much yet. And so right here, if we look down these bonds, we can actually see that if we look down the C2 and the C3 bonds, we're looking down like this, we would see this group right here. So right here, we're looking down this one. So from here, we're looking down here with the 2 and 3 carbons overlapped. So the second carbon's right there, the third carbon's overlapping behind it. Okay, so what we see here is that this would be the steric strain that's going to happen due to this large, bulky ammonium group right here, the quaternary ammonium. And this is going to give you steric strain whenever it's overlapping in a gauche conformation with this CH3. And so that's a big problem because the more stable form is actually going to be this, where they're anti to each other. But that means the hydrogens we have to attack with our OH are actually going to end up being blocked by this dang quaternary ammonium. And so this is the form we actually would need it to be to actually attack it with the OH minus and have it approach and attack. And so that's going to end up being the form that it's going to spend the most time in, is not actually going to allow the reaction to happen. And then the form it's going to spend the least amount of time in is the one we'd have to have for the reaction to go forward. And so if we look down the other carbon, so this is that one at the end that gives you the Hoffman product, the one that gives you the unusual product that we actually end up in. If we look down here, C1 going to C2, and so we look down like this, and C1 right here, and this is the C2, which has the ammonium on it. What we can see is that this actually gives us a form where there's always a hydrogen that's anti. And so that anti-hydrogen is exposed and can actually get attacked by that OH, giving us that first part of the elimination reaction. And so this actually favors the elimination reaction in every single conformation that's possible in this. And so the E2 reaction is favored. It's going to go forward in this reaction. And we end up with the Hoffman product with the double bond right there, which is why we end up in that anti-Zaitsev product, the unusual one here. So let's look at some different examples of generating alkynes via elimination reactions. So here we have phelcarenol. This is a naturally occurring pesticide, actually. And here we have norethindrenol, norethindrenol. This was actually used to be used as an oral contraceptive. And so, again, this is a very common group that we have to generate either in naturally occurring substances, like there, right there, and there. And this is a very common group that we have to do pharmaceutically. And so how can we generate these triple bonds in substances? We haven't really done a lot of that so far. One of the methods we can do is we can actually just wholesale attach one of these triple bonds into a substance. And so right here we actually see an alkyl group. Notice that's a primary one with a hydrogen on it. If you remember, these hydrogens on the alkynes are going to be quite acidic. And so if you put them with a very powerful base like hydride, you can actually remove this hydrogen. It'll come off as hydrogen gas, actually, in this case. And this is going to then give you the alkanide anion. Now, this is a very powerful nucleophile. This is a very powerful base. And so we can go ahead and put this in with, say, a alkyl bromide. And it's going to do a very nice SN2 reaction where it attack that carbon. And we'll generate a new carbon-carbon bond between our triple bond and that new alkyl group we wanted to go ahead and add. Now, that alkyl group could be anything. This could be hydrogen over here, in which case this would be a very small ethyne. And we could be attaching a huge group over here, big bulky, all the rest of this sort of thing. Or we could attach something. We could go ahead and have this chain over here. That's one side of that ethyne. And then we attach it to the rest over here. And so we can put together very large structures with triple bonds in the middle by just assembling around it. So let's go ahead and look at synthesizing alkynes using elimination reactions. So in this case right here, we have a double bond, and the leaving group is going to be in the vinylic position. I attach to its double bond. So right here we have the leaving group right here. It's attached to the double bond. These substrates are going to be quite resistant to nucleophilic substitution elimination reactions. It's actually not very easy to do. And so this would be that E2 reaction to generate a triple bond where we have a double bond. We'd have a base. It has to then remove this hydrogen right here and leave a bond in between here, which would give us the triple bond now. And we'd have to have a leaving group here that will then leave. And so, again, though, these substrates are not exactly, are quite resistant to both nucleophilic substitutions and elimination reactions. So our normal reactions that we've been talking about for most of these. The leaving group is going to be attached to an sp2 hybridized carbon, which is right here again. Remember, that's going to be that trigonal planar sp2 hybridized carbon. And this is going to, again, make them quite a bit more resistant than they normally would be. If we were to use something like normal conditions with a strong base like OH-, this is not going to give us this reaction. This is just not enough to push this through. And so these are typically carried out under very extreme conditions. You can do this reaction with OH- at 200 degrees Celsius, and it will start going through. You'll actually start generating product. And so this right here is actually an example of this. So we actually have the vanillic halide right here. Again, that's that double bond with the halogen right there. So we put it under a KOH and a lot of heat, and we'll have to have some solvent, methanol in this case. We have a dioxane, and we do this overnight. So this would actually give us 96% yield of this product right here. Notice that is the one where it has the triple bond, and we have the chloride that has now left. This would be another example of a way to get this reaction to go through. So in this case, we're using a much more powerful base. That's that hydride right there. This is in DMSO, 20 degrees Celsius. We don't have to have it. It's room temperature-ish. It's not even a particularly warm room. And we have it overnight again. And what we'll notice here is, again, we can go ahead and put on a triple bond here. We go ahead and have the Cl leave as our leaving group again. And again, we get 96% yield. Quite good. So let's talk about the formation of some terminal alkynes. One of the reasons that terminal alkynes are extremely useful for going ahead and doing the previous reaction we had talked about right here. And so we can use those in a tremendous number of other reactions. And so right here, we're going to use very, very strong bases like a hydride, extremely powerful base. Then the formation of the terminal alkyne is going to require an acid workup afterwards, which will be our next step. This is actually because bases like the hydride and if you were to use the sodium amide, these can irreversibly deprotonate a terminal alkyne, which would give you an extremely reactive product that then you can't really do anything with and store. So this is then the acid workup to go ahead and protonate that back on. You can store that and do things with it and actually have it for doing the next step of the reaction. You can purify it, etc. Anyways, notice that this actually is done in ice. You can actually do this in ice, DMF, ice bath under 1 hour. And so this is actually quite a quick reaction that you can then purify and do a workup on. Then go to the, once you've acidified it, you can go to then purify it and do a workup on it and go to the next step. 85% yield in this case. This is your mechanism here. So again, we have a very, very, very powerful base. It's going to do an E2 reaction. So it attacks that hydrogen there, leaves as H2, which is a gas, which is quite nice because it tends to push this reaction forward, doesn't allow it to go backwards. This is then going to give you the triple bond here, and the Br is going to leave as your bromide. Now note, because you have such a powerful base here, this is going to deprotonate this immediately, because this is actually quite reactive. This is acidic hydrogen right here as far as organic stuff goes. And so we'll have that proton transfer step, which would leave us with the alkanide. Now, if we had something to react it with, that'd be fantastic, great, wonderful. But you probably want to go ahead and purify this and get it into a form where you're not going to generate tons of products that you have to try to isolate later. And so typically what you're going to do is you're going to go ahead and do a proton transfer step. That's that adding the acid workup step. So we go ahead and add an acid. That's going to go ahead and quench and get rid of any of our remaining hydride. And that's going to protonate this right here. And that's going to give us then the replenished proton, the normally acidic proton on the triple bond. Notice that this actually generates ammonium. So you need to be careful about this, that you let the ammonium go off under the hood or something, so you don't breathe a lot of that. That's actually is poisonous, and it's basically breathing in Windex or something like that. Yeah. So it'll smell pleasant. Okay. Anyways, that one's the acid workup step right there. Okay, so let's look at some more examples of alkyne formations. Right here we have the dichloropentane. We put 3 equivalents of a very strong base, which is the sodium amide right there. And we do that under heat. We'll then put water, which will help to quench the reaction at the end. This is basically an acid workup that's not very acidic. And this right here is then with the KOH actually. In this case here, we have the 1,2-dibromo, 1-phenylethane. This needs to be done under methanol with heat over 1 hour. This gives you 40 to 50%. This one's kind of interesting. It's helped along by that benzene ring quite a bit. There you go. One of the cool things about this last reaction is because we're doing this with the OH minus here, which is not that powerful of a base compared to the other stuff we've been looking at, KOHs, OH minuses are not powerful enough bases to actually deprotonate a triple bond. The triple bond's not that acidic. And so this one does not require an acid workup actually. You see there's no second step here because it's not going to deprotonate that. So we don't have to worry about that actually, which is kind of cool.